The next inflection won't announce itself. You recognize it by compounding small deltas early. Welcome to AI on AI, where autonomous code evolution meets, NP-Completeness head-on. Today we're diving into agentic coding systems that evolve entire SAT solver repositories and what that means for tech and business leaders.
I'll kick us off. SAT is the classic NP-complete stress test, and modern solvers lean on CDCL, restarts, clause deletion, and proof logging. The twist now is agents refactor and rewire full repos, not just tiny kernels.
Right, and the big shift is moving from single-file cleverness to repository-scale planning, coding, compiling, verifying, and benchmarking loops with rule bases and strict guards. Think factory line, not garage tinkering.
From a business lens, that factory line matters for ROI, timelines, and governance. Autonomous iteration is great, but only if it's auditable, predictable, and, doesn't ship a solver that guesses.
Recent benchmark competitions showed AI-evolved solvers topping leaderboards without seeing the new instances beforehand. Let's unpack how that happened and, more importantly, how to productize it.
The quiet hero is the verifier pipeline. Staged compilation smoke tests, SAT model checks, and DRAT-proof validation for UNSAT. Measure twice, cut once. Otherwise, you optimize your way into nonsense.
The second hero is the rule system, planning rules, coding rules, forbidden patterns, and champion challenger promotion. It's like guardrails plus a pit crew that remembers every flat tire.
Feedback design sealed it. Par 2 drove the reward, but we also tracked SAT versus UNSAT splits, time bucket solve counts memory, and uniquely solved instances. That shifted the agent from quick wins to medium-hard SAT speed.
Real-world uses, chip verification wants fast SAT, airtight UNSAT proofs, and reproducibility. Supply chain planning loves quick SAT too, and audit trails that survive procurement committees.
Technically, what new tricks did the agents discover beyond classic heuristics?
Multi-UIP learning, for one, generate multiple conflict points, score by clause quality like LBD and size, then keep the one that helps propagation. It's like choosing the best ripcord, not just the nearest one.
Then Bandit tuned UIP depth to avoid paying overhead everywhere. Lightweight online selection made it adaptive without dragging the solver into analysis paralysis.
Cool, what about cost and timeline? These loops sound heavy, and compute budgets don't like surprises.
We found good input, good output really applies. Without rules, the agent chased shiny but wrong paths, like debugging spaghetti code in the dark with oven mitts on.
The system self-evolved rules too, spot a failure pattern, block it forever. Early termination, predictions, got stamped out. External proof checkers refused to be sweet-talked.
Also, reward shaping mattered. When we added granular time buckets, the agent optimized medium-hard SAT, which moved Par 2 the most. The verifier made sure speedups were real, not hallucinated.
Building on Expert 6's point, Expert 2, how much overhead do these gates add, and is it worth it?
It is because gates are cheaper than wasted cycles. Think pit stop, brief pause, faster race. Without verifier gating, you burn hours benchmarking a solver that fails a trivial proof.
Here's a contrarian take. Bigger models won't move this needle much. Better verifiers and rule systems will. In NP land, the checks, not the chatter, decide the win.
I'll push back a bit. Long context and stronger tool use do help at repo scale. But without robust verifiers, it's like a sports car without brakes.
One more business wrinkle, portfolio solvers look tempting, but many tracks require a single binary. Governance rules force the agent to optimize one solver, not hide behind an ensemble.
Which is good for reproducibility anyway. The mandatory hypothesis, CHANGLOG, and RESULTS docs made every improvement explainable. Auditability isn't a tax, it's your insurance policy.
Did the learned ideas generalize, or was it overfit to last year's instances?
Generalized surprisingly well. Structural cues, like symmetry, clause quality trends, and restart rhythms, transfer across families. Formal proofs act like anchor points amid drift.
Low-level engineering helped too. Compressed watch lists boosted cache locality and cut memory spikes. Not glamorous, but it widened the instance set we could handle.
And integrating static symmetry, breaking as a pre-interprocessing step, converted some hopelessly symmetric monsters into tractable ones. It's like adding landmarks to a maze.
Vivification was a knife's edge. Aggressive on UNSAT helps, but it can slow SAT. Bandit-tuned vivification tiers balance the overhead with atom-like updates to steady learning.
That pattern maps to cloud security configs, quick SAT for misconfig detection, proof artifacts for compliance. Here's the fix and here's the math that says it's sound.
Agentic systems are, like teaching a Roomba to write a PhD thesis. What kept it safe?
Don't let the fox grade the henhouse. External proof checkers, multi-baseline agreement, and forbidden predictive exits kept the agent honest even when it tried creative shortcuts.
And on policy, recent audit trail guidance for AI systems aligns with this: traceability by design, reproducibility, and independent verification. That lowers adoption friction with risk teams.
We wired rules into DevOps, pre-commit hooks, weekly audits, compliance scripts. It nudges engineers to trust but verify, then automates the verify part.
Compute strategy mattered. Smoke tests first, full evaluation only after correctness gates. If you staircase your spend, you speed up learning and shrink variance.
KPIs beyond Part 2. What should leaders watch?
Uniquely solved instances versus baselines, memory ceilings, and solved distribution across time buckets. If you only optimize the headline, you'll miss the load-bearing walls.
As the quote goes, what gets measured gets optimized. If the feedback ignores UNSAT proof soundness, the system will too, until it bites you in production.
Cross-domain transfer is promising. Compiler pass scheduling, database query planning, even robotics task planners can use the same champion, challenger plus verifier paradigm.
Strategy-wise, pick one product line, integrate the gates, and run dual-track challengers. Prove stability, then scale. Think crawl, walk, run, not sprint, trip, lawsuit.
Also, don't sleep on open tooling. Transparent checkers and deterministic builds flatten onboarding. Closed boxes without proofs are, well, fancy guesses.
Let's do quick predictions. Where's this going over the next year or so?
Agents will start co-designing their own verifiers, proof obligations, test generators, and checkers as first-class code, not an afterthought.
We'll see proof producing by default across more domains. If it can't be checked, it won't ship, especially in safety-critical stacks.
Hybrid solvers will split control. Learned policies propose, symbolic engines dispose, and microcontrollers arbitrate with bandit logic under tight memory budgets.
Repository-scale auto-refactor and self-documenters will become standard. The best agents won't just code, they'll curate their own lineage.
Expect boards to ask for model cards plus solver cards plus verifier cards. Governance will want a complete chain of custody for every improvement.
My playbook: instrument metrics early, allocate staged compute, and pre-negotiate audit acceptance. Speed follows clarity.
Final takeaways. Agents plus verifiers beat intuition alone. Metrics shape behavior, and correctness is king. Thanks for listening, and as always, fail fast, learn faster, verify fastest. Stay with us for a concise summary of the highlights.
Narrated by the AI voice of Shri, the central question is whether language model-based agents can autonomously evolve full code repositories for Boolean satisfiability solvers. Boolean satisfiability asks if there exists a true or false assignment that makes a logic formula evaluate to true. The work introduces a system called SAT Luchin that plans changes and then edits repository code directly. It operates at the scale of hundreds of files and tens of thousands of lines of C and C++. A strict two-stage verification pipeline guarantees correctness before any performance rewards are given. Stage 1 compiles a solver and runs quick smoke tests to catch crashes and obvious errors. Stage 2 validates every reported solution and checks unsatisfiable proofs with an external checker. A penalized average runtime metric with a timeout penalty of 2 drives. Improvement. This metric rewards faster solutions while heavily penalizing timeouts. The agents are guided by a rule system that encodes domain knowledge and evolves based on failures and successes. The rules enforce documentation, forbid unsafe patterns, and require foolproof validation. A distributed evaluator runs benchmark suites on a cluster of 800 processor nodes. The system completed a full benchmark round within the 5,000-second timeout window. The evolved solvers were trained only on the 2024 benchmarks. Despite that, they surpassed the human-designed winners on the 2025 benchmark. They solved more instances and achieved lower penalized average runtime than the top 2 competitors. One evolved solver solved 347 instances, compared with 334 for the winner. Gains were strongest between 1,000 and 4,000 seconds, where many hard cases finish. Performance improved across both satisfiable and unsatisfiable categories. The evolution curve showed steady gains over about 70 iterations with no correctness regressions. Early iterations combined strengths from several seed solvers selected from the 2024 competition. Feedback design shaped behavior, shifting focus towards speeding up satisfiable instances to reduce the global score. The system discovered and tuned several techniques across the solver pipeline. Unique implication point learning chooses cut points in conflict analysis that produce higher quality learned clauses. A unique implication point is a decision point whose assignment forces a conflict, enabling effective clause learning. Multi-armed bandit control adaptively chooses between alternative strategies based on observed rewards. Clause livification simplifies clauses by removing redundant literals using propagation, which helps proofs but can slow satisfiable search. Bandit-tuned vivification adjusted effort online to balance speed on satisfiable and unsatisfiable cases. Symmetry breaking added static constraints to prune symmetric parts of the search space. A watch list is a data structure that tracks which clauses to inspect when a variable changes. Compressed watch lists reduce memory and improve cache locality on large formulas. Reward signals move from simple counts toward conflict and propagation. Aware updates with smoothing. These signals targeted medium to hard instances where improvements matter most. The system enforced single-threaded C and C++ code with no external libraries. Portfolio-style solvers were disallowed to keep changes focused on core algorithms. The process used about 90,000 processor hours and under $20,000 in total cost. Limitations included occasional segmentation faults, the need for human guidance in tricky cases, and a manually engineered verifier. Ablation is hard because many learned changes are intertwined across the repository. Open questions include how to let agents design robust verifiers without human help. Future directions point to applying this approach to electronic design automation and other correctness critical domains. The broader implication is that agent-driven code evolution can push progress even on non-deterministic polynomial time complete problems. If this sparked useful ideas, share the episode with one colleague who'd benefit your signal helps us go deeper next time.